Okay. Well, it's my pleasure to introduce Professor Gray Rybka, who's coming to us virtually from the University of Washington, where he's been since 2007 after having completed his PhD at MIT with Peter Fisher. Gray is a member of the ADMX collaboration that we'll be hearing more about during the talk. But just to give you some context, ADMX is the world-leading experiment in the ongoing search for an ongoing effort to detect Axion dark matter directly in the laboratory. For the students, or any of you, I suppose, who wanted to know more about Axions, I would strongly recommend that you check out the review article published by the Particle Data Group in their booklet. They summarize different topics in high-energy particle physics, Higgs bosons, dark matter, astrophysics, and the article on Axions is particularly good, and it was co-authored by Gray and his colleagues. Gray's also taken a leading role recently in the current SNOMAS community planning process, where the high-energy particle community gets together and tries to decide on the big problems that we want the US effort to be focused on. And Gray has been co-chairing the ultralight dark matter session. Axion dark matter is an example of ultralight dark matter. But Gray's interests extend beyond axions. He's also very interested and has worked extensively on neutrino physics. He's a member of the Project 8 collaboration, which is seeking to measure the absolute neutrino mass scale using precision electron spectroscopy in tritium beta decay. And their results are highly anticipated, and they may be the first to tell us the absolute mass scale of the neutrinos. But that's not, as far as I know, the subject of today's talk. I think we'll be hearing more about axions from Gray just now. So please, Greg, take it away.
Okay, so to take it away, I'm going to click share screen. I'm going to click PowerPoint. I'm going to click from the beginning. Okay, can I get confirmation that you see my title slide?
Yes.
Confirmation, excellent. Okay, well, hello, thank you for the introduction. As I said, I'm Gray Rybka, coming to you live from Seattle in my basement. Though this is a picture of the laboratory where ADMX takes place, and that's just a little bit down the road from me at the University of Washington, at CEMPA, the Center for Experimental Nuclear Physics and Particle Astrophysics. So I'm going to tell you, I guess the search for Axion dark matter is actually a really broad topic now, and I'm going to tell you kind of my small portion of it and make a few mentions of what else is out there. Okay, starting at the beginning, since it's a colloquium, you may recall there's this stuff out there called dark matter, and numerous astrophysical measurements tell us that most of the stuff in our universe, most of the matter is not made out of atoms like you or me or stars or planets or anything in our standard model. If you look at the largest scales, the entire Hubble volume, there's certainly indication that there's stuff out there and it's not atomic, that's gravitating. And it hasn't gone away. If you look at galaxy clusters, you can see let's see, do I have a pointer here? I guess if I use this pointer, no, maybe I better not. I'll just click something. Anyway, so right, the upper left-hand corner of the cosmic microwave background, the lower left there, if you look at galaxy clusters, you overlay colors from gravitationally inferred mass, from actual radiating mass. When galaxy clusters pass through each other, you often see the gravitational mass separates from the gas and dust where we're made out of normal atoms. If you look at nearby galaxies, such as the classic Vera-Rubin style rotation curve, you see they do not follow the standard Keplerian orbits unless you assume that there's this extra stuff out there that we're embedded in this halo of dark matter. And so working our way down, and kind of 10 orders of magnitude at a time, the next step would to say we need to see evidence for dark matter in the laboratory, and that's where it's missing. And so that's the problem I'd like to solve. I'd like to find it in the laboratory. And And to make a new candidate for dark matter, everything in the standard model is pretty much ruled out. But with the new things, it has to be cold. When I say cold, I mean non-relativistic in modern times. In the galaxy, it has to be feebly interacting. So if it was strongly interacting, we would have seen it already with light. We need to produce it in the early universe so that it's there by the time the CMB is being formed. And I'm happy to talk about reasons the different standard model particles don't work if you want to bring them up. So there's lots of ideas out there. The community favors WIMPs and Axions because they both have their own sort of separate motivation coming from outside astrophysics. The one that I'm going to talk about is Axions. Why Axions? Well, to take an old slide now, there are many viable theories out there, and there are many natural elegant theories out there. But if you want a theory to be both, and explain dark matter axions are one of the few non-excluded elegant theories out there. And axions actually came before the dark matter was a big issue. And the idea is, if we look at quantum chromodynamics, the stuff that's holding our atoms together, you look at the symmetries there, and the symmetries that can be and the symmetries that are, you can expect that you might see a neutron electric dipole moment. If you just write down the equation, you say, okay, well, I put in whatever reasonable numbers there are, I would expect to see a neutron electric dipole moment. However, any attempts at measuring the neutron electric dipole moment have been unsuccessful, and they've limited it to 10 orders of magnitude below what one might consider the natural scale for this. This is a very experimental view of it, is what's the thing that you measure. And so that suggests there's something that makes the neutron electric dipole moment unnaturally small, or equivalently that there's something that forces the QCD to have the CP symmetry when it really doesn't have to. And so one explanation for this, probably the best one out there, is a new symmetry called Peche-Quinn symmetry that just explains why QCD would be CP symmetric, and explains why you would not see a neutron electric dipole moment. But as a side effect of this new symmetry, there'd be a new particle. It was called the axion. And at the time, first the idea was, oh, we can look for axions in accelerators. They're probably at the weak scale, because there's this bias among physicists that if there's new physics, it's probably at the weak scale. Wasn't there. And then it was thought, well, if the axion's light enough, then it's really very weakly interacting, and we could just sweep it under the rug. It's great. You invent a new particle, and there's no way to detect it. No problem. And the particular interactions of the axion, for those of you who do accelerator physics, think of it as a pi naught. It has very similar quantum numbers. It's a pseudo-scalar, and the interesting coupling for me at least is this axion couples to 2 photons. So axions can just decay spontaneously to 2 photons, but for the mass scales we're going to talk about, the decay time constant is longer than the age of the universe, so that's not a very significant factor. However, we can use that particular interaction. And the strength of that interaction is pretty much set by the requirement that you solve this strong force CP problem. And that there's a little bit of wiggle room allowed in how strongly axions couple to photons. And there are some benchmark models called KSVZ and DFSZ. There's about a factor of 10, factor of 7 difference between the two. If I had to pick my favorite, I guess I'd pick the DFSZ, even though it's more weakly coupled, it kind of has better unification properties. So let's see. So we've invented this new particle called the axion. It solves some nuclear physics problems. We've made it so light and weakly coupled that it's probably not a problem until you start asking about, well, what would the early universe look like in the presence of axions? As it turns out, passing through this symmetry, as the temperature changes, you dump a whole lot of the energy in the universe into the axion field, and the axion field is decoupled from everything else. And so you're left from the early universe, there's this leftover mass, this leftover cold matter that's with us still today as a form of dark matter. So it's kind of the perfect candidate. It does everything you want. And to have the right properties, if you take the most vanilla models of the early universe, you would say, oh, masses around 1 to 100 micro eV would produce a universe where 100% of the dark matter is made out of axions. So if you start thinking about, well, maybe these are worth trying to detect, you make a plot of axion photon coupling on the y-axis and axion mass on the x-axis. These two things are related by the fact that you're already solving the strong CP problem. And so those lines you see, KSVZ and DFSZ with a yellow band around it, are indicative of where in this parameter space you could find the well-moted, what we call the QCD axion. No one's stopping you from inventing particles that live off of those lines, and we would call those axion-like particles. And conveniently, there's all these different experiments and astrophysical exclusions on axion-like particle space, but there's not a whole lot of exclusions on these true QCD axions down in that mass range I was talking about. Just to give you a feel for what some of these experiments are. At the top, you see the so-called light shining through walls experiments. This is using a magnet to convert laser light to axions and back to laser light, and to try and detect it, like Oscar, ALPS, PVLAS, things like that. Then you could have axions produced in the sun. The sun, as we know, is hot, and hot things, it's very, very energetic in a way that could produce axions just through standard interactions. The axions would then stream out of the sun, where they could be converted to photons using a strong magnet and then detected as kind of KeV photons. And you could see this in there's the classical Axion helioscopes like CAST, or they're working on something called EAXO. And this is also the mechanism for some of the WIMP experiments that have sensitivity axions. Often it is solar axions that would deposit energy in the detector in the similar mechanism. And you can see that's the light blue on this plot. And then finally, there's the green lines that are dark matter haloscopes that presume, if you presume that all of dark matter is made out of axions, then you can convert these axion dark matter into photons. And because there's a lot of dark matter out there, it's a much more strong experiment than trying to get axions that are made in the laboratory, or even axions made in the sun. So I should make, so a decade ago, that was the full story. Those were the games that were in town, and it's a very different story right now to talk about how people are getting very excited about axion-like particles, or wave-like dark matter, in particular, anything with a mass lower than an EV. And there are a lot of ideas out there. I'm going to give you a mass range where I say, okay, this is the right place to look. That's using the most like vanilla arguments you can. If you want to add more features to your theory, you can have axions or axion-like particles of different masses be dark matter or be part of the dark matter story, and you might want to look for those. And so here's just a smattering of the ideas out there. I'm going to tell you about haloscopes, and all of these, the ones in the blue there work similar ways. And they look for the axion photon coupling. There's also a coupling to the nucleon in terms of like a time varying EDM. And so there's things like Casper looking for that. And other nuclear couplings you could look through for even torsion experiments can see them as a fifth force. And not even on here are there's a few ways to look for axions using direct gravitational couplings due to their interactions with black holes. If they get to be the right size, it's very cool. And so there's this whole interesting world out there, and I'm not going to tell you about it. I'm going to tell you about the piece that I feel I'm an expert in. So I'm zooming in here and saying, if I take people who are using the most generic conservative assumptions that I can, they're adding as little as possible to our standard model, and they're taking what we understand from cosmology and predicting what mass of axion would make up 100% of dark matter. I put this on this plot. It's a little bit out of date, but the predictions are still there. So it's a coupling versus mass. So I've zoomed in on that old plot and put some bars between my KSVZ and DFSZ coupling lines. And so so there's disagreement by a little over an order of magnitude. So as an experimentalist, I take that to mean that we need to build experiments that probe this whole range. And so that is what the ADMX G2 experiment's goals are, is to cover a significant portion of this range and explore these very plausible, very well-motivated axion models of this mass and coupling space. So let me step back and talk in general terms how an axion haloscope works. And I did do this when I was teaching in introductory physics, as I really fell in love with this particular experiment that's talking about resonant energy transfer. And and now that I think about it, I could have snuck into the university, stolen this demo. It's not like they're having in-person classes. I could just have it at home. maybe next time. Anyway, when you get two tuning forks and you set them side by side like this, you actually, when you set it up to have this box pointing at each other, so they're not touching, and you tune them to be exactly the same frequency, and you whack one of these tuning forks and it vibrates and hums and the students all listen, and then you give it, you talk a little bit, and then you snatch up the tuning fork you struck, and the other one is still ringing, just as loud if you got it right. And it's always very surprising because they're not touching, it's entirely transferred by sound. And then you detune the second tuning fork a little bit, perform the same experiment, and you get no energy transfer. And so the idea is that if you have two resonant structures and they're weakly coupled, but they're the same frequency, you can transfer a lot of power from one to the other if you're patient to let it get through. And the equations of motion are the same. If I say Axion dark matter is one of my resonators, it's just an oscillating field. Because the Axion really is, it's at this scale, it's a large scale field. The microwave cavity in my experiment has an electromagnetic resonance. It is also a resonator. If they are tuned to the exact same frequency, then the Axion photon coupling, even though extremely weak, is still enough to transfer significant power from one to the other. If instead you are a particle physicist and you are uncomfortable with the idea of the wave equation anymore, then I can just say, consider the Axion as a particle coming into a region with a strong magnetic field. It scatters off the virtual photons in the magnet and produces a real photon, and that real photon bounces around in my cavity, as in this cartoon here, and then gets picked up by this antenna. I'm not sure if I'm really pleased with this diagram, because there's this implied length scale that there's these photons that their wavelengths are the size of the cavity, and the Axion wavelength is larger than the size of the cavity. But sometimes it helps people think about it. So if you're building an experiment like this, you want a kind of as much dark matter in your cavity as possible. So you have a large cavity volume up to the point where you're kind of limited by getting the right resonant frequency. You want the as high of magnetic field as possible to get those virtual photons for your Axions to scatter off of. And you want a highly resonant cavity to get as much transfer as possible. And you're going to be looking for these rare photons produced by Axions in your cavity. And so you want to see these photons above a sea of noise, and that's cavity blackbody radiation, just because there's a physical temperature and any amplifier noise that comes from downstream amplification of these extremely small signals. So I step from there to one slightly more sophisticated cartoon, and I like it better because the Axion wavelength is more reasonable there, even though my photon has gotten is still a little small. But it shows the Axion coming into the cavity, that shows the tuning rods. So we move rods around inside this cavity to change its resonant frequency, and that way you can look for different masses of Axions, because you're looking for different frequencies of photons. And then it shows that you pick the signal up, and what you're looking at is power spectra. So you're looking at power versus frequency, and the Axion would produce a signal that would look like a little bump, and the frequency of that bump would be, h bar omega is equal to roughly the mass of the Axion plus a very small amount of kinetic energy, and that kinetic energy gives it some width, and that's the line width. But so in the end, you build this whole thing, you tune it to different frequencies, and you look for bumps. So here's a picture of the collaboration doing one of these experiments. It's ADMX G2, which is maybe the leading of certainly the biggest and longest running of these experiments. And here is a cutaway view of our machine drawings on the left-hand side, showing some of these components that you should recognize from the cartoon. At the bottom is that cavity with some tuning rods. It sits inside a magnet. Above that, space for refrigeration, space for some very fancy amplifiers I'll talk about, with their own magnet that cancels the field. And then sort of cryogenic infrastructure above that. The cavity and associated equipment come out, and you can see a picture of, I guess that they were actually putting the cavity and components, the insert as we call, into the main magnet. And I'll just talk about some of the technical details of what's going on here. Just to give you a feel for the way this tunes is that you have your cavity. It has a resonant frequency, and we're using the TM010 resonance, which is the one that couples all the Axions. And so you can make a transmission measurement, so you get this Lorentzian line shape of the cavity, and you're sensitive to Axions kind of within 1 Q width of that Lorentzian. And so if you don't see any Axions in a particular spot, you then move these tuning rods, and we're doing this every 100 seconds or so. And shifting the tuning rods changes the geometry of the cavity slightly, and thus shifts the resonant frequency and shifts what Axions you can look for. And so we're doing this many times a day as we slowly scan across frequencies that could be, could be the Axion frequency. And if you do a whole bunch of these rod steps, which we put on the x-axis, and then plot the transmission via color versus frequency in the y-axis, you get what we call a mode map. I like to show it because it's very pretty, and it's just showing that there's a complicated resonance structure going on inside the cavity, and it turns out that in theory, all of these have some coupling to the axions, but in practice, the only one that couples well, and the coupling is determined on how well the electric field, the magnetic field, and the axion field all overlap, is the TM010, which if I remembered how to set the pointer up, I can just draw on it. It's that one. Can people see this?
Yes.
Nice.
Well,
okay.
Barely, but
anyway, it goes
yeah.
well. It's red on red, but anyway.
Yeah.
So we set it up, and then there are the tuning rods over there. Oh, this is great. Now I'm gonna write all over these slides. This is great.
By the way, while you've paused for a minute, Gray, there's a question in the chat. Doug, you just want to ask your question?
So I don't know how to have the chat open at the same time.
No,
so
that's okay. I'll
in charge of disrupting me, please.
What magnetic field do you have in the cavity?
8 Tesla right now.
8 Tesla. Okay, thank you.
Right. Okay. So this cavity, we don't want it radiating, power that's the noise that's going to make it hard to see a signal, and so we want it as cold as possible. And so we use a helium-3, helium-4 dilution refrigerator, and we cool it down to about 100 millikelvin. And so there you see the zoomed-in refrigerator and where it goes when the students are installing it. And so why 100 millikelvin? Well, it turns out there's also the contribution of noise from the electronics. If you buy kind of the best transistor style amplifiers you can get, they contribute a noise equivalent temperature of 2-ish Kelvin, which is too high for us. And so we're working with different amplifiers. And it turns out there's actually a lower limit. If you're using a linear amplifier, there's what's called the standard quantum limit. And if you use this amplifier, you always add a half photon's worth of noise to your measurement, no matter how good your amplifier is. And for us, that's in 50-ish millikelvin range. Here's just a plot showing how one of these amplifiers, you physically cool it down, it adds less and less noise. And then when you get below 100 millikelvin, it doesn't really get any better. And that sets the scale for why we operate at the temperatures we operate. Here's some
quick question, Gray.
Yeah.
When you're talking about the tuning rods, and by changing the geometry, you change the resonance. Over what range can you scan just by doing that? I mean, can you get decades of mass reach?
You can, at least with all the designs we have, you're lucky to get an octave. And so
a what? Sorry,
an octave. You can get barely a factor of 2 in your tuning range, and then you pull the whole thing out and you unbolt the cavity and you buy a new cavity, you machine a new cavity and bolt on a new one. And that octave, the cavity tuning range, funnily you should talk about it, is not even some of these amplifiers have more limited tuning range than the cavity itself. And so there's this series of components that all go into the experiment, and they each have their own frequency range they work over. And so someone has a big spreadsheet where we try and optimize this. But the fact of the matter is we've kind of got it to where every year or so we have to pull the whole thing apart and replace all the components to operate in a new frequency range. And towards the end, I think I'll have some frequency ranges to give you a feel for what that is. Right here, I've got a microstep squid amplifier and a Josephson parametric amplifier. We've used them both. They have their advantages and disadvantages. We're using a Josephson parametric amplifier here. These have fame in that they're, if you're doing superconducting qubits, this is what you read them out with. And the cold electronics is not entirely trivial, but it's not, it's not like as complicated as a kidney here. The signal, see, this is useful because now the signal comes out of our cavity, comes up through these devices, is amplified in our amplifier here, hopefully close to the quantum limit, comes out, gets amplified by a second stage amplifier, and goes out, and that's where we detect it. And then there's all these other parts that come down and are used for calibration of understanding how do we know where the cavity resonance is. We use these things. How do we calibrate the temperature? We use this thing, and we'll talk briefly about all of those. The calibration is I should go back. So we can heat this and we can heat this. We've got little heaters all over the place. And but if you heat things, then our quantum amplifier gets very strange. So you turn this off and you heat these different components, and you watch just the raw power coming out of your experiment as a function of temperature, and they track very well, and you can use a fit to do those two things to figure out what's the noise contribution from downstream electronics with the quantum amplifier off, and you get that. So this was 12 Kelvin, so it's like 2 or 3 Kelvin with some attenuation, so some efficiency hit that you're taking. And then the next thing you do is you turn on your amplifier, you measure how much your gain increases, you measure how much the power just coming out of the experiment increases, and from that you can infer a noise temperature. And this is year before last year's run, and we're getting kind of 300 millikelvin total noise temperature. And this is important because it ties our calibrated temperature sensors to the power coming out, and so that's how we know how many yoctowatts are coming out of the experiment, and that's how we turn that directly into a particle physics measurement of the dark matter density times the axion photon coupling. So that's the primary calibration that goes through that.
There's another question in chat. Yeah. Aaron, do you want to ask your question?
Yes, sure. Does the range of frequencies that you can scan, I guess, drive the sensitivity for your Axion mass, right, at the end?
Let's see. So does the range of frequencies drive? Well, so there's sensitivity to coupling, and for many years the Haloscope community and ADMX worked on getting more sensitive experiments, and so now for any particular frequency we can achieve whatever sensitivity someone wants. If they give us an axion photon coupling, we can hit it. It's a question of how long does it take to hit that particular sensitivity at that particular frequency. And given the theoretical uncertainty is much more on the frequency, we try and become very sensitive, but we also want to scan over frequency space very, very quickly. Is that quite what you were asking?
Yes, it's more or less, yeah. But then, so what do you mean that so quickly? This is a constraint on the experiment setup because you have to change everything again, or?
Yeah. So to achieve the sensitivity of the DFSE axion, I think there'll be some slides on this in a little bit, but it takes about, for any particular frequency, you need about 20 minutes of total integration time, total power measurement time. And so if we somehow could make the axions deposit twice as much power, then we could spend 1/4 of the time. And so if you have to spend 20 minutes at each frequency, so moving the cavity in between, if you were to spend only 5 minutes, then you'd scan 4 times faster, right? So we're literally limited by how long we have to dwell at each frequency setting and integrate for power. That's what limits, in my mind, how long it will take to find the axion, is because there's a lot of frequency range to scan. In 10 slides or so, I think I can show you roughly our plans for the future, and I'll spitball some ideas of in years how long it takes to cover things. But yeah,
okay, thank you.
All in the tuning times.
Great. Sorry, could you remind us the process you're studying? Is that 1 axion in and 2 photons out? Is that the process you're driving or hoping?
It's 1 axion in and 1 photon out. And the photon in between comes from the magnetic field. So I said axion to 2 photons. So it's more like an inverse Primakov, where one of the photons, it's the standing magnetic field that counts as it. So it's a 1-to-1 correspondence in terms of mass, mass in and frequency out.
I see. And then the fact that the frequency has to be within your range of, let's say, a factor of 2, how do you decide to focus on 1.5 gigahertz instead of 20 times that or half that?
Oh, well, so, all right, I try not to go back, but I think I can go. All right, note here on my plot of, so we're starting at the lower end here, right? About 4 microeV, I think. If I go up here to my frequency, that's 1 gigahertz. So this is kind of, 800 megahertz. And then we'd like to go up as far as this. And so we're working our way this way. And the cavity has maybe a 50 kilohertz bandwidth. So it, on this plot, the cavity bandwidth is a delta function. It's very, very narrow. And we're moving that every 100 seconds is the exact motion. So we're working our way to cover this region. But this is years of work. I mean, so this was the first year of work, and by the end of this talk, I'll show you what the second year of work was. and then I'll claim the third year, or that COVID happened. Let's cut time in half. So the next 2 years, and I'll draw that. Does that give you a feel for where we're talking about in terms of frequency?
Well, this was right. This was related to Andrew's question for how how much dynamical range you have, and I guess the question is why is it by design that it's so narrow? Because you want very high sensitivity. Why can't you just broadcast a white light, quote unquote, in that entire range and just see when that blip comes up on it?
Okay. So the power from the Axion is enhanced by the cavity resonance by its Q. So if my Q is high, I get a lot of Axion power, but I have a very narrow range over which I can explore. If I choose to degrade my cavity Q, I get much less power out, but I can look over a wider bandwidth at any given time. If I go back and do the math to say just scan speed over a fixed range of frequencies, the scan speed is going to be proportional to Q. So it's actually more efficient to operate with a high Q and a narrow bandwidth where you move your cavity frequency a lot than it is to make an intentionally broadband device. I mean, yeah, and I wish it wasn't so, because a lot of the trouble is in cryogenic motion and frequency stability, when I would really, it'd be nice if I could just make a broadband thing and flip a switch and then come back in a month or two. But it turns out you can't find it that way, at least in this frequency range. At the lower frequency ranges, there are tricks you can play with broadband systems. Okay, where did I leave off? Right, I wanted to talk about so the raw data coming out of this looks like power spectra. And so there's a 100-second raw data example in the upper right-hand corner here, where it's some measure of power. We don't normalize it because we later on we normalize it from our temperature calibration versus frequency, and that gives you a feel for what how much we record. It clearly has some shape. We know what that shape is. That has to do with our electronics, and we subtract it off, and then we scale things by the cavity line shape. So we're less sensitive out here, which is why you've got big wiggles, and more sensitive in here where you're right on the cavity line shape, because the cavity line shape looks like this. This is really, I'm never going to do an in-person talk again unless they give me a box of crayons so I can draw on their screen. Right, so there's a modest amount of analysis work to get the raw data into a power spectrum. And so once we've got these power spectra, or rather, I guess I should say the process of getting these power spectra is you get many of these power spectra. You take 100 seconds, move the rods, 100 seconds, move the rods, get 100 seconds, move the rods. You've got many power spectra, and you ask, okay, given all these power spectra basically added together and reweighted by where the cavity is, are there excesses, are there bumps that could be an Axion signal? And the answer is there's always bumps. There's always statistical bumps for one, and for two, there could be intrusive signals like somebody's cell phone. And then finally, there's always synthetic Axions. So we have a red team that has an electronics box that's always plugged into the experiment that can inject signals through a second, as a third antenna. And so we always have these, making sure that yes, we would see something if it was there. So we have all these, what we call candidates, and we go back and rescan these candidates. So we take more data in those. So if we have a 3 sigma excess, you take twice as much data, and it becomes either a 5 sigma or it becomes less. And so statistical excesses can be gotten rid of pretty quickly. And a hint of so I guess that in conclusion is we never have a hint of a signal. This is an advantage over the poor WIMP experimenters who run for years and open the box, and then there's just a slight excess, and the conclusion is, well, we've just got to run for years and years more, build a bigger experiment. This is more like looking for the J-psi in an accelerator. You're tuning and tuning, but once you've found the right frequency, we'll very quickly have a signal that'll be clear as day. And so we rescan to try and get that, and we subject the candidates to a variety of confirmation tests. So is it persistent and it's always on? That's what we expect for dark matter. It's not correlated to any signal that we can detect outside the experiment. Does it follow the cavity line shape? Is it truly coming from the cavity as opposed to some downstream electronics? Does it follow the magnetic field squared, which an Axion signal one? Those are some examples of what we do. And so here's a pretty plot of showing lining up a whole bunch of raw signals with, these are computer generated synthetic signals, just to show what it would look like And so the KSVC signal here, you would actually see it in a single spectrum, and it would be very clear. The DFSC signal, you actually have to do all the averaging before you can get it. But regardless, with the amount of data we take, we should have signals will be very significant, and we're able to hopefully find the most plausible models of Axion dark matter if they're out there, if we hit the right frequency. I'm going to give a story about one that we did find, and that this is one of these synthetic signals. And we have kind of two categories of synthetic signals. There's a semi-blind one that's injected, but as soon as we've detected it, it's confirmed, like, oh, this is synthetic, you can move on. And then there's categories where the team keeps it close to their chest while the detection committee evaluates the evidence and makes a plan for, okay, we're going to ramp the magnet down and this is our series of tests we're going to check. And that has to be done before that's revealed that it's actually a synthetic. And so here's an example of one where we found it in the blue data, and then we did a rescan with the orange data, and its significance improved, and it was well past our candidate threshold. And so this is what gives us confidence that we'll find it if it's out there. And that's kind of this happens every few months, so we're always on our toes. A short note about the exact shape of the line width of the Axion signal we're looking for. The most conservative assumption is that it's a Maxwell-Boltzmann, all dark matter has the same temperature, and it's kind of as hot as it can be without falling out of the galaxy. And that gives you this green curve in terms of, or there's the purple curve in terms of the line shape. There are some models out there, like basically any model that adds more sophistication becomes a bit more narrower, and that actually makes it easier to detect because narrow signals are easier to see. There's less noise in the background. And so we show our limits to both of these to get a feel for what's the spread from our uncertainty in the way dark matter is put together. There's often questions about what are the requirements of an Axion signal, because there are a lot of human-made signals in this bandwidth where we don't need to worry about radioactive decay, but we do need to worry about Wi-Fi and phones. We do have many layers of metal shielding, so very few gets through. But that which does, usually you can either detect it in the room outside the field, or it persists all the time, or it doesn't follow the cavity, or it's not properly suppressed in the different modes of the cavity. So the kind of the form factor is wrong, or it doesn't scale with the magnetic field squared. And we've so far, we've never actually had a signal where we had to turn the magnet down and verify it was not a real Axion from that. So we've only made it partway through this list. And then finally, at the very end, once we have a signal, we expect to see some daily and annual frequency modulation as the Earth turns and goes around the sun and moves through the dark matter halo. So that'll be an interesting thing to study once we've made a discovery. So having said all that, where are we in terms of published limits? So this is our results as of March. So this was the first, the orange here, this is the first year that we were able to operate with sensitivity to this DFSZ Axion model. So everything up into this point was a little speculative. At this point, we feel like there's a good chance of finding Axions if we're at the right frequency. I should probably point out the y-axis is labeled here as Axion photon coupling. What we actually can measure is Axion photon coupling times dark matter density. So this is Axion photon coupling times a plausible dark matter density of 0.45 GeV for CC. So if we make a discovery, it'll be hard to disentangle those two, but that's, it'll be a great problem to have. Right, and so the next year we were able to cover a much wider mass range and make more exclusion limits on the Axion space. We didn't find anything, but we have kept running since then, and so we're now operating at higher frequencies in the hopes of finding something. Because in the end, the game is about discovery. It's not actually about producing limits. So to give a feel for where are we trying to go with all this, here it is zoomed out, covering kind of that region of the theoretically exciting space. And you can see the blue there is kind of older versions of ADMX. There's some dark gray that are previous haloscopes. Orange and green are same as the last plot, the last couple of years of ADMX running. The light blue is where we are operating right now. We were very fortunate to turn the experiment on just before the lockdown started. And so we've been able to keep it kind of limping along. And so we've been able to keep acquiring data. And we'll continue to do so for until something goes wrong. We've all got to go into lab and fix it. And then looking to the future, the experiment will continue to operate up to 2 gigahertz. We've got development for a 2 to 4 gigahertz modification to the experiment. I'll talk a little bit about what's going into that, and then the hitting 4 to 10 gigahertz is clearly going to take R&D, but we've got R&D being worked on there. I'll talk some about it because that's some of the fun development. Right, so why is it harder to get to higher frequencies? Why are we at the frequency we're at? So as you get to higher frequencies, the natural cavity size decreases. Smaller cavity size, smaller volume, there's less dark matter inside, just naturally there's less power out and it's harder to see. Just because of the surface area to volume ratio, the resonator Q gets worse, and so things get more broadband, but the signals are smaller, and so you lose out in terms of scan speed. And then the standard quantum limit corresponds to it's a half photon, and so as your photons get more higher frequency, more energetic, the noise in proportion to the signal gets bigger. So all of these make it harder to work, and so how are we going to counter these? So we can work on more sophisticated resonators. We can work on amplifiers that evade the standard quantum limit in various ways. One can get bigger magnets than 8 Tesla, though, once you get to 20 or so, things get very, very expensive. And then there's ideas of how to increase our resonator Q to counter the high frequency Q loss. So some of my favorites of these this one is actually, this is like basically built. Is moving from a single right circular cylinder cavity to this more sophisticated apparatus of 4 cavities, where each cavity has its output signal combined in a phase tracking way, so that you basically recover the whole volume back and get 4 times the signal coming out, and that's how we'll operate in the 1 to 2 gigahertz region. And for the 2 to 4, we've got ideas where you get truly a large number of very small cavities that are all added together and all tuned together with their own unique challenges. We've got some small cavities working already in that range. There's an example of what we call the sidecar cavity that was operating in the 4 to 6 gigahertz range, using different modes that coupled the Axions at different strengths. We were actually able to publish some new exclusion regions in Axion-like particle parameter space. We weren't sensitive to QCD Axions because it wasn't, we didn't have the quantum limited amplifiers hooked up. And every year, this system, we kind of add, we add things that are not quite ready for the main system to get them ready. So this year, we've got some of these fancy wideband quantum amplifiers, so moving beyond JPAs to TUPAs, and I think we figured out how to break them, but they were actually operating really well for a while. Looking into feedback systems to increase the power, and looking at new frequency ranges. Talking about even higher frequencies requires even more outside the box ideas. And one of those is moving beyond the standard quantum limit. So the standard quantum limit comes because we're measuring a standard radio frequency signal. We're measuring a sine wave. You measure a sine wave, you want to know the amplitude, you want to know, where's the phase, where does the sine wave cross the x-axis? And no one cares what the phase of the Axion signal is. For one, it drifts all over the place, and for two, it's not involved in discovery at all. And it turns out that the amplitude and the phase are quantum conjugate variables, and so the standard quantum limit is just an expression of you're trying to measure 2 things at the same time that you shouldn't. What would be much better is instead to just count how many photons come in at a particular frequency, irrespective of phase. And one way to do this is shown here, is you basically hook up your cavity to what is a prototype qubit. So this is work being done at University of Chicago. And so you hook this up, and you by making non-demolition measurements of this qubit, you decide whether or not there are excess photons inside your cavity to the frequency you've chosen. And this turns out to in theory have there's no standard quantum limit, and so you can cool your system to much lower temperatures and get much less noise, which is very exciting and would be enabling technology for these higher frequency searches. on the cavity front, there's things that resonate electromagnetically other than just cavities. And so here are just some examples with things that were played with in my lab. Open resonators that have many, many nodes, things with spatially varying magnetic fields that are being explored. That are all kind of, they're all very neat. And the one on the right is actually, there's a big experiment in Germany using a semi-resonant open system called Mad Max that I think might be going in this direction. So yeah, so there's a lot, there's a lot of R&D to do to cover the whole frequency range, but we're getting there. So let me wrap up and then I can move on to questions. The conclusion is the Axion is really well-motivated dark matter candidate. It's really worth looking for. It's one of these now more than ever things because it's not become any less well-motivated over the years. And so more people are starting to look for it. And with the ADMX experiment, we were finally able to probe some of the theoretically best motivated places, and we're the first experiment to do it. So we very much hope to make a discovery sometime soon. And failing that, we've got a pretty solid set of plans to cover more and more of this plausible frequency range until we've either found it or excluded it completely. So thank you. I'll shift over to questions now.
Let's before questions, let's turn off our mics and thank Gray for the nice talk. Thank you, Gray. I see Aaron has raised his hand. Would you like to go ahead, Aaron?
Yes. For the multi-cavity, how you will handle the correlate noise of cavities?
Let's see. So for the multi-cavity system, one hopes that thermal noise from the different cavities is uncorrelated while the signal is correlated, and that should get us an advantage.
Can you? I would expect the opposite. Why is that the case?
Well, so thermal noise is typically uncorrelated. If you have two things that are physically separated, that are just that are blackbody radiation, they should know nothing about each other. They shouldn't be entangled. They should be uncorrelated thermal noise. The signal should be correlated because it's coming from the same Axion field, and the Axion wavelength is much larger than your experiment. So it's like, if you're looking at, I don't know, a megahertz radio wave and you have two antennas that are just separated by a meter, then you expect those antennas to be very, very strongly correlated because they're probing the same thing.
Also, the advantage is that the wavelength is too large then, basically.
Yeah. The Axion wavelength is extremely large.
Okay. Thank you.
Doug, do you want to ask?
Can I ask a quick question?
Yeah, thanks. So I was
Doug go first.
very nice talk. I was wondering, is there, I mean, maybe you would, well, two questions. One is, what's the Q of the cavity? And the second question is, and maybe you said this and I missed it, is there any advantage, do you gain anything by having electron density in the cavity? Like, would this ever help you? Because I can imagine a scenario where you use some kind of, say, transparent insulating magnet where it's got some large internal magnetic field just because of the magnetic order of the material. And you could imagine tuning the resonance in another way rather than by sticking stuff in a vacuum cavity.
Let's see. So the Q is 100,000 unloaded on a good day. That's from copper walls. So is it useful of an electron density? There's actually many ways to take that question. If you look at, say, the Quacks experiment, and they are looking for actual Axion electron couplings of a sample sitting inside the cavity, and the cavity is something where they pull that coupling, the signals from those couplings out. That's probably not what you were asking. There's a paper on the archive, a tunable plasma Axion haloscope, where they want kind of nano wires to give an electron density, and they do that to basically shift the resonant frequency significantly, so you can support a much, let's see, for your volume, the frequency can be much higher than it would be in vacuum, I believe is their setup.
Okay.
And this one's sort of controversial because I looked at that and said, it's going to spoil your Q. And they're like, no, it's not going to spoil the Q. So that time will tell about that. That'll be very interesting. But that's one place where people talked about electron density.
I just meant like if you have if your cavity has a dielectric in it, some sort of, as opposed to vacuum, right? Do you win or lose if you
lose.
You lose.
It just you end up taking a hit by from usually the loss of the dielectric. It's not without precedent though, because we have these issues. So the cavity has many resonances, and we're mechanically manipulating it, and so you get mode crossings, you get avoided crossings, regions where you cannot acquire good data that you trust. You would be able to calculate your coupling to the Axion. You may have noticed there were gaps in the limits I showed you. Those were due to these avoided crossings. In the past, in different designs of the Haloscope, we have gotten through those by getting close to the crossing and then filling the system with liquid helium, which changes the dielectric constant, and it kind of different modes get shifted in different directions, and then we're able to scan over that region. The current setup is not designed to do that. Unfortunately, if you dump a bunch of liquid helium on a 100 millikelvin system, it's incompatible. But it's been done before, and for a good effect.
Okay, thank you.
Yeah, I mean, sort of along the same lines, I seem to remember, maybe by reading the PDG article on Axions, that one of the cast experiment, I thought the helioscope has some mode where they fill it with plasma, and then they're getting an enhancement, a resonant conversion by dialing the plasma frequency.
Yeah. This is so they're dialing the wavelength of the gamma rays to better match the wavelength of the high energy axions, and they fill it with helium-3, I think, for some reason.
I see.
And so that gives them slightly higher mass sensitivity than they normally would. And they did that just to hit that EV. They were able to just hit some QCD predicted range with that.
I think Mudit had a question.
Yeah, I had a question. It may not be directly related to what you told us today, but these exclusion plots that you presented, they're assuming that all of the dark matter is coming from these axions, right?
Yes. So when I say an exclusion plot on coupling, that is with an assumption of dark matter density. If dark matter is if only 10% of dark matter is made of axions, or if dark matter is only 10% of what we guess it is locally, then my couplings sensitivity is reduced by a factor of 10.
Okay, so these curves that I'm seeing, like for example, this pink band on which you're trying to operate on, that band sort of goes up?
No, sorry, the pink band is a theoretical prediction of coupling. The colored regions, like the green and the orange, are the limits. The limits become weakened if the axions are not 100% dark matter.
So how do these bands, like what kind of analysis goes in like in drawing these bands?
Oh, the KSVZ and DFSC bands are you talking about, or the limit?
Yeah.
Oh,
no,
yes.
These.
Oh, the KSVZ and DFSC they come directly from you take the strong CP problem, you write out Peche-Quinn symmetry.
Oh, so you're dealing with QCD axions in particular.
Yeah, it's coming out straight from the QCD axion.
Okay.
And the only wiggle you have is I believe KSVZ axions only couple to quarks, and DFSC axions they also couple to leptons.
Okay. So I guess that since you constrained yourself to be for a particular QCD axion, for example, you only have one parameter left, like for example, the Peche-Quinn scale.
Right, which
so that gives you so that gives you a constraint. I see. Okay, thanks.
I have a question. Am I on?
Go for it, Randy.
Can you hear me? Yeah, okay. It seems like your sensitivity would be a lot better at higher frequencies, where you could make a superconducting cavity with very high Q, and you're above the thermal noise floor. Higher the frequency, the more immune you are to thermal noise.
Well, so the not sure if I agree with you that I'm more immune to thermal noise. So certainly the standard quantum limit noise, like the half photon, gets bigger and bigger energetically as I go up in frequency. So my noise takes a hit there.
But I guess your your temperature is low compared to the frequency. So doesn't that count for the line width?
Let's see. So it is true. So I can get over the edge on that. You know, I can get over the edge of the curve. I can get, you know, into the you know,
tail.
catastrophe region. I think in the end, in terms of my sensitivity, it doesn't help a lot unless I can then count photons one at a time, which is one of the reasons we're working on that. And then as for superconducting cavities, the trick is getting a superconducting cavity to work inside an 8 Tesla magnet, which is, you know, I used to say that, oh, you know, you're not going to run a superconductor inside a magnet. That's crazy. But there are some papers out that are very, you know, very curious about high TC superconducting cavities aligned in very specific ways. That may be a path in the future.
Yeah, you could imagine a detector that was made from Rydberg atoms that you could tune exactly using electric or magnetic fields and be probably close to 100% quantum efficiency.
There was an experiment called CARAC that made progress on that maybe, you know, 10 years ago, and then it kind of got hung up. Though I think there's a group at Yale. I think Raina Murayama is looking into whether to resurrect that, because you're right that's another example of a microwave photon detection technology that does not suffer from the standard quantum limit that I do.
Okay. Yeah, thanks.
Like Mustafa was going to ask a question.
I think you already mentioned this, but if I want to go to lower axion masses than than what is shown here, what is the prospect for that?
Yeah, so if I were doing that with exactly the experiment that I've got now, at the bottom of my range here is when my cavity fills. Oh, I can't draw on this. Oops, I lost it. Can you still hear me?
Yes.
Okay, good. I will just keep talking. I'll stop touching the screen now. The lowest frequency on that plot corresponds to the cavity filling our magnet entirely. And so you have to buy a bigger magnet, which is, you know, larger volume magnets become more expensive, but they're conceivable, you know, up to factors of 2 or 3 bigger than ours. And then the next thing you do is you build instead of a microwave cavity resonance system, you make something more akin to an LC circuit style resonator, which there's some ADMX members working on. There's also abracadabra and DM radio experiments there's, you know, resonant or semi-resonant, and some are non-resonant ways of getting a haloscope-like Axion to photon conversion if you wanted to be looking at nano EV axions. And then finally, if at that level, you can also consider looking for axion nucleon couplings with time varying EDMs of various materials, like the Casper experiment. These are things that are not, you know, they're not like running like ADMX, but they're ideas out there and are being refined and getting in prototypes.
Thank you.
Is it possible to go back to the summary slide, because I had a question on that?
Can I ask?
Yes, I got there.
Oh yeah, go for it. Actually, go ahead, Aaron.
Yeah, so for the frequency analysis, have you tried any machine algorithms to share for signals like self-organized maps or something like that?
So we've thought about it a little bit. The analysis is not super complicated compared to many of the things. Like in the end, it really is a bump hunt. There's a one-dimensional plot of power versus frequency, and you're looking for a particular line shape. And so there's not a whole lot beyond just, oh, I make a matched filter and run it. There's interesting analysis to be done if you're looking for non-standard models, especially ones with very narrow line shapes that are moving around as the Earth turns and trying to correlate things taking at different times. Those might be right for those sorts of algorithms. Yeah,
but I mean, you can even try, because if you run your filter, you are also biased by the shape that you are putting in, right? But if you can do some self-organized map, this is unsupervised learning, so you can look for, I mean, any potential new signal that is out of what you have in the filter, right? So
Yeah, so it's true. I mean, if you pick a filter, you guess the wrong width, you take a sensitivity hit if the signal is actually broader or narrower. We have pretty good astrophysical arguments that our signal can't be much broader. Because if the signal is broad, that suggests there's a wide velocity dispersion in dark matter. And if the velocity dispersion is too wide, then it's not gravitationally bound to the galaxy. And so that's just not going to work with astrophysics. So we're actually looking for the broadest thing possible. And so our limits that we set are the most conservative. But we could do a lot better if we knew that the line shape was narrower. So there might be some opportunities there. Yeah, I mean the narrower the line shape, the more interesting the analysis gets.
Okay, thank you.
Let me ask one quick question, then we can turn it over to wine and cheese. I mean, looking at the summary plot, it looks very different than the types of summary plots we see for WIMP dark matter direct detection up at, dark matter masses around the massive nuclei, where there were at a point dozens of experiments clamoring to have the strongest limit, and now they've merged into a handful of mega experiments like Xenon 1 ton. So is it, I'm getting the impression, and I've generally had the impression that ADMX is kind of out on their own doing these microwave cavity searches at this well-motivated mass window for Axion dark matter. Why aren't there
So
3 or 4 other collaborations around the world doing exactly what ADMX is doing?
So yeah, so what you said about being kind of out on its own was true a decade ago, and it is no longer true. And so the answer for one is that most of these experiments are just getting started, and they have not released results, but a few of them have, and these plots are out of date. Let me go back to the very beginning, the most up-to-date one I have, and just to show respect for people who are doing the same thing, I will throw out some names. Yeah, this is not so bad. Doesn't have. All right, so these are the what's going on. These are all precursors, mostly to ADMX, done at Fermilab, Rochester, Brookhaven, Florida. But these are all like 80s, 90s experiments. So let's take, this right here, this is the haystack experiment at Yale that's actually done some very interesting work with squeezing. There's missing around, I think they're around here, but I'm not sure, is the CAP. There's a South Korean Center for Precision Physics, Axion and Precision Physics that has been spinning up. They've taken a while to get up to speed, but they actually have some results that were released this summer that are around here. There's an Australian group that's now an ADMX collaborator that actually ran something here. It's super narrow, but it just kind of proved a principle to set it up. Okay, those are the ones that are actually putting things on the map. And but the like I said, ADMX is kind of more mature, and so the results are just early for these, and they're narrow, and the field is shuffling and reorganizing, and like you said, there will probably be mergers and things in the near future as the community is kind of gelling around. Oh, this is really compelling physics. It's been compelling physics for a while. We should really get together and start building some really serious experiments for looking for this, and ADMX is the first in there.
Great. So we'll do wine and cheese in a minute. Let's pause one more time to thank Gray for the very nice talk. Thank you, Gray.